Good morning, everyone. So in this video today, we will be going over some derivatives and their proofs. We will not prove all of the derivative rules, but we will prove some of them. So before we start, I just wanted to remind you of the definition of a derivative, which is what I wrote up here. It's limit of f of x plus h minus f of x divided by h as h approaches 0. So today, the first derivative we will be stating and proving is the derivative of a constant. So first let's write the statement. Derivative of a constant equals 0. I will highlight the statements I write today. Now let's prove it. So if we have a function, f of x equals to a constant c, and I want to find the derivative of f of x, so we use the definition of the derivative, the same one I wrote above. Now, one thing to point out, f of x equals to c. There is no x involved in the function. It's just a constant c. So whether we are dealing with f of x plus h, f of x, or f of something else, f of anything will be c. So this limit is equivalent to the limit of c minus c divided by h as h approaches 0. This becomes the limit of 0 divided by h as h approaches 0, and 0 divided by h is 0. Now 0 is a constant, and we already agreed that the limit of a constant is the constant itself. So the limit of 0 as h approaches 0 is 0. And this is how we prove the derivative of a constant. Now we will move on to the power rule. As the name suggests, it's a power, so it's x to the power of something. For today we will say x to the power of n. To find the derivative of x to the power of n, we drop down the power, so it becomes nx, and x is to the power of n minus 1. For example, if I want to find the derivative of x cubed, I draw this here means derivative, the prime sign up here. So I drop the power, so it becomes 3x to the power of 3 minus 1, which is 3x to the power of 2. Now this is the statement, and now we will prove it. So we will prove this power rule using the following. We will prove it using the fact that x to the power of n minus a to the power of n equals to x minus a times x to the power of n minus 1 plus x to the power of n minus 2 times a plus x to the power of n minus 3 times a squared plus x times a to the power of n minus 2 plus a to the power of n minus 1, and these are n terms. So we will use this statement and we will begin with our proof. So, as usual, we start by defining the function. Now we are proving the power rule, so x to the power of n. So we define the function f of x equals to x to the power of n. So for this proof, we will use the other definition of a derivative, which is, I will remind you of it right now, it's limit of f of x minus f of a divided by x minus a as x approaches a. Now let's plug in what we know. So f of x is x to the power of n, f of a is a to the power of n, and we divide this by x minus a. Now again, we use this fact that I told you about, and we know that x to the power of n minus a to the power of n is this entire thing I wrote here. So I will copy it and write it below. So I get the limit of x as x approaches a of this entire thing divided by x minus a. And as you might notice, we can cancel x minus a and x minus a from the numerator and the denominator. This leaves us with limit as x approaches a of x to the power of n minus 1 plus x to the power of n minus 2 times a plus x to the power of n minus 3 times a squared plus dot 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 plus x times a to the power of n minus 2 plus a to the power of n minus 1. Now, so as usual, when we solve a limit, we can always plug in to see what we get. So let's plug in a. If we plug in a, we get a to the power of n minus 1 plus a to the power of n minus 2 times a plus a to the power of n minus 3 times a squared plus dot 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 plus a times a to the power of n minus 2 plus a to the power of n minus 1. And I'm just reminding you that these are n terms. Now using exponent rules, a to the power of n minus 2 times a, we add up the powers. This is a to the power of n minus 2 plus 1, which is a to the power of n minus 1. Same thing here happens. A to the power of n minus 3 plus 2 is a to the power of minus 1. And the same thing happens here. And again, a reminder that these are n terms. So we have the same term that's being added and added and added n times. So this is n a to the power of n minus 1. We will move to the derivative of a constant multiplied by a function. So derivative of c times f of x, we can take the constant out. It becomes c times derivative of f of x. In order to prove this, as usual, we will start with defining a function. So I will define the function this time to be g of x equals to the constant times f of x. Now I will take the derivative of g of x. This is the derivative of a constant times f of x. And as usual, we always go back to the definition. In this case, we use g here, not f. So g of x plus h minus g of x divided by h. The limit of that as h approaches 0. This is equal to the limit. So let's look at g of x plus h. So it becomes c times f of x plus h minus g of x is c times f of x divided by h. And as you can see, we can factor the c from the numerator, and we get c times f of x plus h minus f of x divided by h. And with limits, with limit laws, we can always take the constant outside of the limit to give us limit of f of x plus h minus f of x divided by h as h approaches 0. And I hope you recognized what this is. This is the derivative of f of x. So it is f prime of x. So the derivative of a constant times f of x is the constant times the derivative of f of x. Now let us learn about the derivative of a sum. First we will look at a sum and then we will make it more general in order to learn the proof of a derivative of a difference as well. So first of all, the derivative of a sum f of x plus g of x is the derivative of f of x plus the derivative of g of x. So in order to prove it, I will define a function s of x to be f of x plus g of x. So the derivative of s of x is equal to the derivative of f of x plus g of x. Now, as usual, let's go to the definition, which is s of x plus h minus s of x divided by h. Now let's replace what is s of x plus h. This is f of x plus h plus g of x plus h. Now what is s of x? S of x is f of x plus g of x. All of this divided by h. Now, let's continue. It becomes f of x plus h plus g of x plus h. The negative goes to each term, minus f of x minus g of x, all divided by h, which becomes limit of, here, as you might see, we have f of x plus h minus f of x, and we have g of x plus h minus g of x. So we can split this into two fractions. Let's do that. So we have f of x plus h minus f of x divided by h plus g of x plus h minus g of x divided by h. Now using limit laws, we can split the limit. So we get limit of f of x plus h minus f of x divided by h as h approaches 0 plus limit of g of x plus h minus g of x divided by h as h approaches 0. And if you noticed, this first term is the derivative of f of x, and this second term is the derivative of g of x. And this is the proof for the derivative of a sum. Now let's generalize this proof to make it fit the proof of a difference as well. So the first thing to note, to generalize this proof, I will put a plus minus sign here and the plus minus sign here. So the derivative of f of x minus g of x is the derivative of f of x minus the derivative of g of x. And I will let s of x be f of x plus minus g of x. So let's continue. So the derivative of s of x is the derivative of f of x plus minus g of x, which is the limit of s of x plus h minus s of x divided by h as h approaches 0. And again, this becomes the limit of f of x plus h plus minus g of x plus h minus f of x plus minus g of x divided by h. So now this becomes f of x plus h plus minus g of x plus h minus f of x. Now instead of the plus minus g of x, because I have a minus multiplied by these signs, it becomes minus plus. So I switch the signs. It becomes minus plus g of x. So this gives us the limit of f of x plus h minus f of x divided by h plus minus g of x plus h minus g of x divided by h. So we factored out the plus minus. So then we can split the limit into two limits. So it becomes limit of f of x plus h minus f of x divided by h as h approaches 0. Again, plus minus the limit of g of x plus h minus g of x divided by h as h approaches 0. So this, in fact, this first term is the derivative of f of x, and this second term is the derivative of g of x. Let's move to the derivative of sine x. So I will start by telling you the statement that the derivative of sine x is in fact cosine of x. Now there are a few limits that you are supposed to know in order to be able to do this proof. So the first one, we have proved this sine of x over x, the limit of sine of x over x as x approaches 0 is 1. And for the sake of this specific proof, we will replace x by h. Now we already proved this in a previous video. Now a consequence of this is the fact that the limit of cosine of h minus 1 divided by h as h approaches 0 equals to 0. I will show you the proof of this limit because we have not proved it before. Basically, the limit of cosine h minus 1 divided by h as h approaches 0, what I will do, I will take the negative of the numerator, so it becomes 1 minus cosine h, and I put a negative sign outside, so nothing basically changed. So 1 minus cosine h divided by h. Now I will multiply this by 1 plus cos h in both the numerator and the denominator. This is a minus b, a plus b. So now I get a squared minus b squared, which was 1 squared, which is 1 minus cosine squared of h. And in the denominator, h times 1 plus cos of h. Now let us continue. What can I do with 1 minus cos squared of h? Basically, we learned earlier some trigonometric identities. Sine squared plus cosine squared of x is 1, and for our cases we're using h. So 1 minus cosine squared of h equals to sine squared of h. So I will write here sine squared of h divided by h times 1 plus cos of h. So this gives us, I can separate the sine as sine of h times sine of h. And in fact, I can write this as sine of h divided by h times sine of h divided by 1 plus cos h. Because this is multiplication, I can write this as two fractions multiplied. I can write this as one fraction. I'm just separating it for the sake of the proof. And what happens in here is that I can separate the limit into two limits using limit laws. So this becomes limit of sine h divided by h as h approaches 0 times the limit of sine h divided by 1 plus cos h as h approaches 0. Now the first limit is the limit that we have just proved in an earlier video. It is equal to 1. Now let's look at the second limit, which is the limit of sine h divided by 1 plus cos h. So as h approaches the 0, let's plug in 0 and see what happens. So in fact, the sine of 0, sine 0 equals to 0, and cos of 0 equals to 1. So if I plug in h equals to 0, I will get on the numerator 0 divided by 1 plus 1. So 0 divided by 2, which is 0. So this limit gives me 0. So 1 times 0 is 0. And now, using these two facts, these two limits that I have right here, I will prove the derivative of sine of x. As we do usually, we always start by defining a function. Let f of x equals to sine of x. So the derivative of f of x, and again, let's start with the definition. This is f of x plus h minus f of x divided by h as h approaches 0. So what is f of x plus h? This is sine of x plus h. F of x is sine of x divided by h. This is limit as h approaches 0. Now, you might remember from a property earlier that sine of x plus h, so this is sine of x times cos of h plus cos of x times sine of h, and then we keep the minus sine x. Again, if you're confused by what I just did right now, feel free to watch a previous video in chapter 1 about trigonometric identities. And here, limit as h approaches 0, from I can factor out, as you can see, there's a sine x here and the sine x here. I can in fact factor out the sine x. So this becomes sine x times cos h minus 1. And this term here stays the same, plus cos x sine h divided by h. Moving on, I can in fact split this into two fractions. So this is my first fraction, and this is my second fraction. And now that I have an addition between them and I have two fractions, using limit laws, I can split the limit. So now I have two limits. And now let's proceed. So you know the variable we are dealing with here is h. So with respect to h, sine x is in fact a constant. So let's take sine x out. And now I'm left with limit of cosine of h minus 1 divided by h as h approaches 0 plus, again here, cos x is a constant because it has no h in it. So plus cos x times limit h approaches 0 of sine h over h. And these are the limits we just proved earlier in this box up here. So the first one, the first limit, in fact, cos h minus 1 divided by h, the limit is 0. And the second limit is 1. Sine x times 0 is 0, cos x times 1 is cos x. Cos x plus 0 is cos x. And we just proved the derivative of sine of x. Now let's move to cosine of x. So let's let f of x equal to cosine of x. I will write the statement here. ddx of cos x equals to negative sine of x. This is the statement, and let us prove it right now. So first of all, the derivative of f of x equals to the derivative of cos x. And this is, let's start with the definition. And now, what is f of x plus h? F of x plus h is cos of x plus h. F of x is cos of x divided by h. And now this limit becomes, if you remember from previous trigonometric identities that we learned, cos of x plus h is cos of x times cos of h minus sine of x times sine of h. and then we keep the cos x here, all divided by h. And now you might have noticed that we have cos of x here and cos of x here. We can factor cos of x. So cos of x, this leaves us with cosine of h minus 1, and then we leave the other term the same. And now we have two terms in the numerator. We can in fact split this into two fractions, as we did with the proof of sine earlier. And since we have two fractions, we can now split the limit. So now we have two limits. Again, as we did with sine before, this proof of sine. So here h is the variable that we're interested in. Since cos x does not have any h, then cos x is a constant. And in the second limit the same, since sine x does not have any h, then sine x is a constant. So we can take the constant out, and this leaves us with limit of cos h minus 1 divided by h as h approaches 0. And we take the sine x out, this leaves us with the limit of sine h divided by h as h approaches 0. And these are the limits we proved earlier today. We proved these. So the limit of cos h minus 1 divided by h as h approaches 0 is 0. And the limit of sine h divided by h as h approaches 0 is 1. So cos x times 0 is 0. Sine x times 1 is sine x. So this leaves us with negative sine of x. Now we will look at the product rule. So we are looking at the derivative of f of x times g of x. This is equal to f of x times the derivative of g of x plus g of x times the derivative of f of x. Let's look at the proof right now. We will define a function p of x equals to f of x times g of x. The derivative of p of x, which is the same thing as saying the derivative of f of x times g of x. As usual, we always start with the definition. This is equal to the limit of p of x plus h minus p of x divided by h as h approaches 0. And now what is p of x plus h? This is f of x plus h times g of x plus h. And what is p of x? P of x is f of x times g of x, all divided by h. And now we will do something that's a little bit tricky. First, we will keep the first term the same, and then we will add a term into the numerator. So I just wanted to point out that if I were to add, let's say, plus a, and then I do minus a, I technically did not change anything because plus a minus a, this is 0. So I just added 0 to my numerator, and this is what I will be doing. So I will add the term, I will start with a minus, so I will add minus f of x plus h times g of x plus f of x plus h times g of x, and I will leave the last term the same. All of that divided by h. Now, if you're asking why I did that, let's take a closer look. Now I have f of x plus h here, f of x plus h again here, and I have g of x here and g of x here. Why am I showing you this? Is because now we can factor. So we can factor f of x plus h to get g of x plus h minus g of x. And we can factor g of x to get f of x plus h minus f of x. all of that divided by h. And as we did in earlier proofs, we can always split this into two fractions. So now I have two fractions, each of these fractions divided by h. And again, using limit laws, I can split the limit and here I have another limit. And after doing so, maybe it's nice to even split the fraction, maybe just to look at it in different ways. So I will write f of x plus h times g of x plus h minus g of x divided by h. I didn't do anything, I just separated the term f of x plus h. So this is still the same thing, just for the sake of having a clearer proof. And now one thing I can do with this, again using limit laws, is I can also split the limit here. This is a product. I can split the limit. So limit of f of x plus h as h approaches 0 times the limit of g of x plus h minus g of x divided by h as h approaches 0 plus the limit of g of x as h approaches 0 times the limit of f of x plus h minus f of x divided by h as h approaches 0. And now let's solve each of these limits. So the first one, f of x plus h, the limit of f of x plus h as h approaches 0. As we always do with limits, we can always try plugging in. So if I plug in h equals to 0, I will get f of x multiplied by this limit here. This is the derivative of g of x plus limit of g of x as h goes to 0. There is no h in g of x, so g of x is technically a constant. So it remains g of x. And the last limit I have here, this is the definition of the derivative of f of x. And now we will move on to the quotient rule. So the derivative of a quotient, so the derivative of f of x divided by g of x is equal to g of x times the derivative of f of x minus f of x times the derivative of g of x divided by g of x all squared. So another way you can try to memorize this, maybe for the numerator, one of the ways I use to memorize this is low d high minus high d low. So low means the denominator. It's the first term up here. D high means the derivative of the numerator. High is the numerator. Minus high, so the numerator. D low, so times the derivative of the times the derivative of the denominator. All of this divided by the denominator squared. So this is the quotient rule. And now we will use the quotient rule to prove a couple of other derivatives. So let's start with the derivative of tan of x. So the derivative of tan of x equals to secant squared of x. So in the proof, as usual, let us define a function. So let's define a function f of x equal to tan of x. And now we will find the derivative of f of x. So the derivative of f of x is equal to the derivative of tan of x. And as you might know, tan of x is sine of x divided by cosine of x. Now using the quotient rule, let's find the derivative of this quotient. So this is the denominator, which is cosine x, times the derivative of the numerator, so times the derivative of sine of x, minus the numerator, so minus sine of x, times the derivative of the denominator, so times the derivative of cos of x, all divided by cosine squared of x. And now this becomes cos of x times the derivative of sine of x, which is cos of x, minus sine of x times the derivative of cos of x, which is negative sine of x, all divided by cos squared of x. And this becomes cosine squared of x plus, because we have a negative here and a negative here, it becomes plus sine squared of x, all divided by cos squared of x. And as you might notice that this numerator, which I circled, is a trigonometric identity because sine squared of x plus cos squared of x is 1. So this is 1 divided by cos squared of x. I will put the squared outside, so 1 divided by cos of x all squared. And we can rewrite 1 divided by cos of x as secant of x all squared, which is secant squared of x. And now we will move to the derivative of secant of x. So the derivative of secant of x is secant of x times tan of x. And again, I will define a function f of x to be equal to secant of x. And now let's find the derivative of f of x. The derivative of f of x is equal to the derivative of secant of x, which is equal to the derivative of 1 over cos of x, because secant, we can rewrite this as 1 over cos. Let's use the quotient rule. So the denominator times the derivative of the numerator, so cos of x times the derivative of 1, minus the numerator times the derivative of the denominator, so minus 1 times derivative of cos of x, all divided by the denominator squared, so all divided by cos squared of x. So this becomes cos of x times the derivative of 1, so times 0, because 1 is a constant, minus 1 times the derivative of cos of x. The derivative of cos of x is negative sine of x, and we keep the denominator the same. So 0 times cos of x is 0. Negative 1 times negative sine of x is positive sine of x, all divided by cos squared of x. This becomes sine of x divided by cos squared of x, and we can in fact rewrite this and split the fraction into two fractions that are multiplied. So we get 1 divided by cos of x times sine of x divided by cos of x. And if you are wondering why I did that, is because when I do that, I can now rewrite 1 divided by cos of x as secant of x, and sine divided by cos of x as tan of x. And now let us move to the proof, the derivative and the proof of cosecant of x. So the derivative of cosecant of x is negative cosecant of x times cotangent of x. So, as usual, to prove this, let's start by defining our function. Let f of x be cosecant of x. Now the derivative of f of x is equal to the derivative of cosecant of x. We can write cosecant as 1 divided by sine. So this is the derivative of 1 divided by sine of x. And here we use the quotient rule, so the denominator, sine of x, times the derivative of the numerator, which is 1, minus the numerator, which is 1, times the derivative of the denominator, which is sine of x. So all of that divided by the denominator squared, so divided by sine squared of x. Now the derivative of 1 is 0, and the derivative of sine of x is cos of x. So I get sine of x times 0 minus 1 times cos of x divided by sine squared of x. And sine x times 0 is 0, 1 times cos of x is cos of x divided by sine squared of x. And 0 minus cos of x, I get negative cos of x divided by sine squared of x. And this, as we did earlier, we can split into two fractions that are multiplied. So we can put the negative outside. This gives us negative times 1 divided by sine of x times cos of x divided by sine of x. And if you noticed, 1 divided by sine of x is cosecant of x, and cos of x divided by sine of x is cotangent of x. And now we will move to the derivative of cotangent of x. So the derivative of cotangent of x is equal to negative cosecant squared of x. And now let's move to the proof, again using the quotient rule. So we start by defining the function, let f of x be equal to cotangent of x, and let us find the derivative of f of x. This is equal to the derivative of cotangent of x. And as you might know, we can write cotangent of x as cos of x divided by sine of x. And here we have a quotient, so we can use the quotient rule. This derivative is equal to the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, all divided by the denominator squared. So divided by sine squared of x. So the derivative of cos of x is negative sine of x, and the derivative of sine of x is cos of x. And this leaves us with negative sine squared of x minus cos squared of x, all divided by sine squared of x. And we can factor out the negative in the numerator, which leaves us with negative, open parentheses, sine squared x plus cos squared x, divided by sine squared of x. And again, you might have noticed that this in the numerator is a trigonometric identity, which gives 1 divided by sine squared of x. And I can rewrite this. I can take the squared outside, so 1 divided by sine of negative 1 divided by sine of x all squared, and 1 divided by sine of x I can rewrite as cosecant of x all squared, which I can finally rewrite as negative cosecant squared of x. And we will now move to the chain rule. So let's say we have a function h of x, and h of x is equal to g of f of x. We can write this as g of f of x. Both notations are okay. So the derivative of h of x is equal to the derivative of g of f of x, which is equal to the derivative of g evaluated at f of x times the derivative of f of x. Now, this is one of these rules that writing it down is quite like writing the statement down maybe is not always understood. So I will show it to you with an example. So let's say we have let's say we want to take the derivative of cosine of 2x. The derivative of cosine of 2x, again, as we wrote up here, first we start with the derivative of g evaluated at f of x times the derivative of f of x. So for cos of 2 of x, what is the derivative of cos? It's negative sine, and we evaluate it at f of x. So we evaluate it at 2x, and then we take the derivative of what's inside. So we take the derivative of 2 of x, which is 2. So we can write this as negative 2 sine 2x. So let us look at another example as well. Let us say we want to take the derivative of negative 3. Let's write this down. Derivative of negative 3 sine 4x squared plus 5. First, negative 3 is a constant. We can always take it out. So let's ignore it for now. Now, what we care about is the derivative of sine of 4x squared plus 5. So what you do, you take the derivative of this outside function. Derivative of sine is cos. You evaluate it at what's inside. So you evaluate it at 4x squared plus 5. And then you take the derivative of what's inside. So the derivative of 4x squared plus 5. To take the derivative, we learned this before. So first of all, 4 is a constant. You keep it out. Derivative of x squared, you drop the power. And x becomes x to the power of 2 minus 1. So x to the power of 1. And the derivative of a constant, derivative of 5 is 0. Let's simplify this. 4 times 2 is 8x. So this is another example about that. So now let's generalize, using the chain rule, we will write a general power rule. So the general power rule is just, as the name suggests, it's a general way of writing the power rule. Because earlier we learned that the derivative of x to the power of n is n of x to the power of n minus 1. Now, what if it's not x that's being raised to a power? What if it is f of x? So let's say I want the derivative of f of x to the power of n. So, same thing, I drop the power, and I get n times f of x all to the power of n minus 1. Now what changes is that I also have to multiply this by the derivative of f of x. So let's look at an example. So what if our function is 2x squared plus 3, and all of this is squared. And I would like to take the derivative of all of that. First thing I do, I drop the power. So I get 2 times 2x squared plus 3, all to the power of 2 minus 1, which is 1. And then I multiply it by the derivative of what's inside. So inside I have a constant. I leave the constant. Derivative of x squared, I drop the power, and I get x to the power of 2 minus 1, which is 1, plus the derivative of 3, which is 0. So I don't have to write this. And just to simplify, 2 times 2 is 4, so here I have 4x. And now we would have learned the chain rule and the general power rule. Please note that starting from this proof, you will need what we call implicit differentiation. So if you still don't know what that is, please check our other video about derivatives. So now we will move to the proof of arcsin of x. The derivative of arcsin of x is 1 divided by square root of 1 minus x squared. So we will start by defining y to be arcsin of x. And the derivative we want, so when we reach y prime, which is the derivative of y, we would have gotten our answer. So we will take the sine of y and the sine of arcsin of x. So we are taking the sine on both sides. We get sine of y equals to sine of arcsin of x, and as we learned in previous videos, sine and arcsine cancel each other, and we will be left with sine of y equals to x. And now we will take the derivatives of both sides, so derivative of sine of y and the derivative of x. So as you might notice that the variable we are taking the derivative with respect to is x. So the derivative of x on the right side is 1. However, the derivative of sine of y is cos of y times y prime, so times the derivative of y. And then, if we would like to solve for y prime, because this is what we do in implicit differentiation, let's solve for y prime, we get 1 and 1 divided by cos of y. Now, we would like to rewrite cos of y in terms of sine, because up we have x equals to sine of y, so we want something that has sine of y, because whenever we see sine of y, we can replace sine of y with an x. So let's use trigonometric identities. We know that sine squared of y plus cos squared of y equals to 1. So let's solve for the positive, for the absolute value of cos of y. So cos of y equals to square root of 1 minus sine squared of y. Notice that y equals to arcsine of x, and as we discussed in previous videos, this means that negative pi over 2 is less than or equal to y, which is less than or equal to pi over 2. This suggests that cos of y is greater than or equal to 0. Therefore, y equals to square root of 1 minus sine squared of y. So the reason I did this, so now we can rewrite square root of 1 minus sine squared of y. Instead of sine squared of y, we can now write x squared. So this is 1 divided by square root of 1 minus x squared. Let's move to the derivative of arctan of x. It's slightly simpler. So the derivative of arctan of x is 1 divided by 1 plus x squared. Again, this uses implicit differentiation. We define y to be arctan of x. We take the tangent of both sides of the equation. We get tan of y equals to tan of arctan of x. Again, tangent and arctangent, they cancel each other. We get tan of y equals to x. And now we take the derivative on both sides. So the derivative of tan of y equals to the derivative of x. Again, the variable we are deriving with respect to is x. So the derivative of x on the right side is 1. And on the left side, the derivative of tan of y, it's secant squared of y. And because we have a y here, we have to multiply this by the derivative of y. And since this is implicit differentiation, we should solve for y prime. So y prime is 1 divided by secant squared of y. Again, a reminder of the trigonometric identities that 1 plus tangent squared of y equals to secant squared of y. So secant squared of y, we can rewrite it as 1 plus tan squared of y in the denominator. And then, instead of the tangent squared of y, we defined earlier that the tangent of y is x. So we can use this, and instead of writing tangent squared of y, we write x squared. So this is 1 divided by 1 plus x squared. We will now move to the derivative of log base b of x. So the derivative of log base b of x is 1 divided by x ln of b. To prove this, we will start by the function f of x equals to log b of x. So the derivative of f of x is the derivative of log b of x. And we will start with the definition, which is the limit of f of x plus h minus f of x divided by h as h approaches 0. Now, what is f of x plus h? This is log base b of x plus h. And what is f of x? This is log base b of x. And we will continue. We will separate 1 of h, 1 over h. We will put it as a fraction multiplied by, so we will separate the denominator and the numerator. We get 1 divided by h multiplied by log base b of x plus h minus log base b of x. And then, using log rules, we have log base b of x plus h minus log base b of x. Keep in mind that there's a minus sign here, so this becomes, and we have the same base, so this becomes log base b of x plus h divided by x. Now x plus h divided by x, we can rewrite this as two fractions with the same denominator. We can write this as x divided by x plus h divided by x. And the x divided by x is 1, h divided by x remains h divided by x. One slight change I will do with the 1 divided by h, I will write this as 1 divided by x times x divided by h. Notice that this is the same thing because in multiplication, if I have x in the numerator and the denominator, they would cancel out and still give me 1 divided by h. So I'm just doing this to help me with the proof. Because when I do this, I can notice that 1 divided by x has no h in it. So I can take, it's a constant, I can take it outside of the limit. This leaves me with 1 divided by x times the limit as h approaches 0 of x divided by h times log base b of 1 plus h divided by x. So again, as you know, with log rules, if I have a constant here or a number, I can take it to the exponent. So x divided by h becomes in the exponent, and now we get log base b of 1 plus h divided by x all to the power of x divided by h. I will continue making some slight changes with this until we reach the final answer we want. So this becomes 1 divided by x. What I will do now is I will switch the limit and the log because log is continuous. So I will switch the limit and the log. I will get 1 divided by x times log base b of limit of 1 plus h divided by x all to the power of x divided by h as h approaches 0. And now, the exponent, I will work with it. X divided by h is the same thing as saying 1 divided by h divided by x. Just to show you, 1 divided by h divided by x is 1 times x divided by h, which is x divided by h. So they are the same thing. I can rewrite this. And the reason why I'm rewriting it this way is because I want to reach something, which is e. The definition, by definition, e equals to limit of 1 plus 1 divided by n all to the power of n as n approaches infinity, which is equal to the limit of 1 plus m to the power of 1 divided by m as m approaches 0. And we can notice that this second one here is what we have. So we have the limit as h approaches 0 of 1 plus h divided by x all to the power of 1 over m. So 1 divided by h divided by x. Therefore, we will continue and we will write this as e. So now we have 1 divided by x times log base b of e. And what can we do with this? We can change the base. Using log rules, we can write this as ln of e divided by ln of b. And what is ln of e? Ln of e is 1. So this leaves us with 1 divided by x ln of b. And this is our proof. And the final derivative proof we will look at is the derivative of a to the power of x. So the derivative of a to the power of x is a to the power of x times ln of a. This proof will use implicit differentiation. So first of all, let's start by defining y equals to a to the power of x. So this is the same thing. So if I were to solve for x equals to log base a of y. Now I take the derivatives on both sides. Derivative of x equals to the derivative of log base a of y. Again, we are differentiating with respect to x. What is the derivative of x? It is 1. What is the derivative of log base a of y? We already proved that the derivative of log base a of y is 1 divided by y ln a. We proved this earlier. However, we have to multiply it by y prime because we are differentiating with respect to x. So we have to multiply it by y prime, and this is implicit differentiation. And now we solve for y prime. Y prime is equal to y ln a because y ln a is multiplied by 1. And then what do we know about y ln a? What do we know about y? Y is equal to a to the power of x. So instead of y here, I write a to the power of x. So I get the derivative of y is a to the power of x times ln of a.